All right, let's jump right in. Today, we're unpacking Chapter 6 of our math text, and honestly, it's less of a traditional lesson and way more like a detective journey through the secret language of numbers. We aren't just going to sit here and look at equations, we're actually going to expose the hidden architecture right beneath them. It's all about finding the strict rules that totally govern things that might look completely random at first glance.
So here is a really quick roadmap of our investigation today. First up, decoding number patterns. Then we'll look at the power of parity, parity in basic math, solving grid puzzles, and finally, wrap it up with sequences and number play.
Starting right off with Section 1, decoding number patterns. Okay, I want you to take a really close look at this puzzle, straight from the source. We've got this line of children drawn as little stick figures, and they are calling out numbers. Now, why in the world is the first person calling out 0? And then, why is the tallest person also calling out 0, while the others are calling out 1s and 2s? How are these kids deciding exactly which number to shout based purely on where they are standing in the line?
And this right here just brilliantly illustrates the whole puzzle. Notice how simply changing the height order of those exact same kids completely changes the numbers they announce. Like in that first setup, the tall red figure says 0. But in the second setup, he's still saying 0, but the yellow figure right behind him is suddenly saying 5. The text is basically challenging us to realize that these numbers represent a very specific relational rule. It's information encoded entirely by height and position, and you don't even need to know anyone's actual measurements.
Which leads us perfectly into Section 2, the power of parity. This is the master key for solving these patterns.
We call this master key parity. It sounds like a fancy academic term, but the crucial point is that parity literally just tells us if a number can be perfectly paired up, or if there's always one left over. Think of it like this. If you have a pile of objects and you can give every single one of them a buddy, that quantity is even. But if you have one lonely object just sitting there left over at the end, that quantity is odd. I know it sounds incredibly basic, right? But trust me, this simple true or false property is about to become our absolute best investigative tool.
The book actually nails this visually. As this character realizes, we can visually prove what an odd number is. It's not just a squiggly digit written on a page. It's essentially a perfect set of pairs plus or minus a single oddball. If you take any even number and just add 1, you break that perfect pairing. It immediately becomes odd. Thinking about numbers in this highly visual way as just pairs and leftovers is going to make solving really complex problems so incredibly easy for us.
All right, Section 3, parity in basic math. Let's see how we actually use this concept as a secret code in everyday arithmetic. If we compare adding 2 evens versus 2 odds, the visual representation is actually pretty stunning. 2 even numbers are really just 2 groups of perfect pairs. So, obviously, pushing them together just gives you a bigger group of perfect pairs. The result is always going to be even. But if we add 2 odd numbers, we can visually see that those 2 leftover oddball pieces, one from the first number, one from the second, they actually find each other. They join together to form a brand new pair. This is exactly why an odd plus an odd always magically results in an even number.
And this handy table summarizes all those exact rules the chapter outlines for us. We've just proven that the sum of any 2 odd numbers is always even. Now, conversely, if you add an even number, which remember has 0 leftovers, to an odd number, that single leftover from the odd number remains completely unmatched. Therefore, an even plus an odd is always odd. And the exact same logic applies straight across to subtraction too.
Okay, let's put on our detective hats and test this out with a mini-story directly from the text. We've got Martin and Maria. We know their ages are consecutive numbers, meaning one follows right after the other, like 10 and 11 or 25 and 26. So here's the question. Can their combined ages ever add up to exactly 112?
Well, using our parity rules, we can confidently declare this situation completely impossible without doing a single complex calculation or setting up some long algebra equation. Just think about it for a second. Consecutive numbers always mean one of them is even and the very next one has to be odd. And what did our rule just tell us? An even plus an odd always results in an odd number. Period. Since 112 is firmly an even number, the math absolutely forbids their ages from adding up to 112. No way! We just solved it instantly using nothing but the property of parity.
Moving right along to Section 4, Solving Grid Puzzles. Equipped with our new tools, it is time to tackle those visual grid puzzles that really stump the students in the chapter.
Take a look at this blank grid and ask yourself this. If you had a massive grid, let's say it was 135 rows by 654 columns, do you really need to sit there and count every single tiny square? Or even calculate the final massive product, just to know if the total number of squares is odd or even?
Nope, the text gives us this brilliant shortcut based on multiplication. You literally just look at the dimensions. Because an even number is made of perfect pairs, multiplying any number by an even number will always yield an even result. Always. So, if at least one dimension of your grid is even, the total number of squares is guaranteed to be even. A 135 by 654 grid? Well, 654 is even, so boom, the total is even. You literally only get an odd number of total squares if both dimensions are odd. Now things are going to get just a little trickier. In this specific grid puzzle from the book, you have to place the digits 1 through 9 into the boxes so they add up perfectly to the numbers in the yellow circles. But our job is to figure out why some of the grid configurations presented to the students are fundamentally impossible to solve, no matter how hard you try. Before you start blindly plugging numbers in and hoping for the best, logic dictates that we set some boundaries. What's the absolute smallest possible sum for a single row of 3 boxes? Well, it's using the lowest digits, 1 plus 2 plus 3, which equals 6. And what's the absolute largest? Using the highest digits, 9 plus 8 plus 7, which gets you 24. By establishing these hard upper and lower boundaries right out of the gate, we can instantly spot that if a grid demands a row sum of 5, or say 26, it's a trick question. It is mathematically impossible.
And here is the real kicker, the hidden symmetry governing these valid grids that the characters Kishore and Vidya figured out. If you add up the digits 1 through 9, the total is exactly 45. That means the sum of your 3 rows must equal 45, and the sum of your 3 columns must equal 45. Therefore, the grand total of all those yellow circles around any valid grid will always be exactly 90. It is just this gorgeous hidden mathematical balance governing the whole puzzle.
Finally, Section 5, Sequences and Number Play. Let's look at how parity behaves when numbers start looping into endless patterns. Instead of caring about the actual numbers here getting bigger and bigger, I want you to focus purely on the parity of each number in this famous expanding sequence. 1, 2, 3, 5, 8, 13. Can you spot the secret rhythm that's just hiding right there in plain sight? Look at the sequence parities. Odd, even, odd, odd, even, odd. Why does it repeat exactly like that? Because every single new term is simply the sum of the previous 2. An odd plus an even makes an odd. An even plus an odd makes an odd. And an odd plus an odd makes an even. It is a completely beautiful rhythmic cycle driven entirely by those same basic addition rules we learned earlier. Which brings us to the very end of our chapter investigation. But I'm going to leave you with one final provocative puzzle directly from the text to chew on yourself. Imagine a light bulb is currently switched on. A character named Dorji toggles its switch exactly 77 times. Will that bulb finally rest in the on position or the off position? Think about the starting state, think about what a single toggle actually does, and most importantly, think about the parity of the number 77. Use the tools we built today, and you won't even need to flip a single switch to know the answer. Until next time, keep looking for those hidden patterns.